9.1 Introduction. This chapter introduces the learner to deserts, their global distribution and factors for their formation. Deserts occupy large parts of the Earth's surface and host different plants and animals that are endemic to these regions. Approximately 41% of the Earth's land surface is covered by drylands. 4. Environmental geology, which are inhabited by 2 billion people. In this, almost 20% is degraded. So a large population is under threat from the process of desertification. Desertification processes affect approximately 1.9 billion hectares of land and 1.5 billion people worldwide. The Gobi Desert is also facing severe desertification problems. It is reported to have degraded land and many villages due to its fast rate of desert expansion. Desert ecosystems have their own biodiversity and the organisms are adapted to survive and tolerate such high temperatures and conserve water. The Thar Desert in Rajasthan covers the largest state in area, 10.4% of the total area, in India. The region receives little rainfall and the temperatures can go up to 55 degrees Celsius, making it very hot and dry. Let us now learn the definitions of deserts and desertification. We will also introduce you to the characteristics of deserts. 9.2 Definitions. Deserts. They are subtropical arid regions where potential evaporation is approximately greater than 2,000 millimeters and the annual precipitation is about less than 200 millimeters. Desertification. It is the process where land is degraded and becomes relatively dry, arid and loses water bodies, vegetation and wildlife. It can be caused due to climate change and through human-induced activities. The United Nations Convention to Combat Desertification, UNCCD, has defined desertification as land degradation in arid, semi-arid and dry subhumid regions resulting from various factors, including climatic variations and human activities. 9.3 Characteristics of deserts. Dry climate and nature of precipitation. In desert areas usually the rate of evaporation is more than the rate of precipitation. There are arid regions that receive precipitation less than 10 to 15 inches per year and semi-arid regions that receive precipitation 10 to 25 inches per year. Sudden heavy storm downfall and flash floods are common in deserts. Causal factors of dryness. Deserts lack in vertical air movement, so no air cooling and no atmospheric condensation takes place. For example, the subtropical latitude deserts such as Sahara, Arabian and Australian. Deserts are characterized by semi-permanent high-pressure systems and high-level temperature inversions. High landscape erosion potential. This is due to lack of vegetation and sudden intense rainfall events. So surface erosion occurs in deserts and water erosion is dominant. 5. Environmental geology. Weathering. Physical weathering is dominant in deserts and chemical weathering is minimal due to the absence of water. Salt wedging, thermal expansion, frost wedging, and plant rooting are some of the processes involved. Also, the weathering process is much slower than in humid regions. Poor soil development. The soil development is very poor. Salts and pedogenic carbonate development is observed. The soils are thin and lack a good amount of extensive organic matter. Impermeable surface layers. This is due to the bedrock, salt beds and hardpans. With the result there is little infiltration and more surface runoff. Drainage patterns. Deserts mainly have ephemeral streams that flow either seasonally or during storms. 9.4 Types of deserts and the global distribution of deserts. Let us now learn about the types of deserts and the distribution of deserts worldwide. Deserts occupy almost 25–30% of the total continental land area. Hence this forms a major part of all climatic regimes. All deserts in the world are not sandy deserts. Only 20% of the Earth's deserts are sandy deserts. There are also stony deserts, i.e. the Kalahari Desert, which consists of large exposed rocks. Hot deserts. These are situated near the equator. The temperatures during daytime can be more than 38 C and the nights are very cold. Examples of hot deserts are the Great Sandy Desert and the Simpson Desert in Australia. Cold deserts. They are found away from the equator in the center of continents. They are characterized by high mountainous areas. As the name indicates, these deserts are covered by snow and ice during winters. Examples of cold deserts are the Patagonian Desert in Argentina and Antarctica. Inland deserts. These deserts are found far away from the sea. They form in the center of large continents where they are protected from the blowing winds. When clouds over the oceans rise over mountains, rainfall occurs. Then the air left is dry. When this air moves inland, no rainfall occurs. This is the reason deserts in the center of Kalahari and Australia are dry. Coastal deserts by the sea. They are found on the west coast of the Earth's continents. These deserts have warm summers and cool winters. Hence they are referred to as cool deserts. Some examples are the Namib Desert in southwestern Africa and the Atacama Desert in South America. From cold oceans the water does not evaporate quickly in comparison to warmer oceans. When air is blown from a cold ocean to the coast it has no moisture, so there is no rain. During daytime the water evaporates from the land, leading to desert conditions. During the night fog forms as the land cools and some moisture in the air condenses. Cold ocean currents flow up the west coast of Africa, Benguela Current, and South America, Humboldt Current, from Antarctica. This cold water interrupts the water cycle, resulting in the formation of the Atacama and Namib deserts. 6. Environmental geology. Semi-arid deserts. These deserts receive 250 to 350 millimeters of rainfall. The summers have temperatures of 20 degrees Celsius and 30 degrees Celsius and are long and dry periods. More than one-third of Australia is a semi-arid desert. Subtropical deserts. These are located at latitudes near or above the Tropic of Cancer and Tropic of Capricorn. These include the following. Tropic of Cancer. The deserts include the Great Sahara Desert of North Africa and the Arabian Desert of the Middle East. Tropic of Capricorn. The deserts include the deserts in the Australian interior, and the deserts in the interior pampas of Argentina. G. Mid-latitude deserts. These deserts include the Gobi Desert of Central Asia and the deserts in the western interior of the United States. Activity. Locate the deserts in the world using an atlas. Write down the biodiversity of these deserts. Visit the meteorological department near deserts and collect the data for past few years. The data can include rainfall and temperature details. 9.5 factors for desert formation. The planet's air circulation patterns and wind patterns are important factors for desert formations. Earth's air circulation patterns. Most of the deserts are located between 15 to 30 degrees north and south of the equator. Here the trade winds blow offshore. The warm air holds more moisture than cold air. Warm air rises at the equator and then cools. This cool air has less water holding ability, so precipitation is common at the equator. The dry air mass moves north n 30 degrees and south s 30 degrees. At plus or minus 30 degrees dry air sinks and warms. This warm air can hold more water, resulting in evaporation of water and desert formations. Hence the equatorial region is tropical and plus or minus 30 degrees is desert. An example is Sahara Desert. B. Rain shadow effect. When hot rising air approaches a mountain, it cools. This cool air that crosses over the mountains is dry. Hence deserts are formed on the other side of the mountain range. There is little precipitation on the leeward side, also called as rain shadow area desert. An example is the Gobi Desert. C. Distance from the ocean. This is also an important factor for desert formation. When land is far away from oceans, then deserts form. 7. Environmental geology. Near cold ocean currents. The cold ocean air warms as it passes over continents. The warmer air holds more moisture and causes evaporation and the formation of deserts. 9.6 Fluvial processes in desert. The significant agents of erosion and transportation in deserts are the flowing waters. Let us study in detail the fluvial processes. 1. Erosional characteristics. In deserts, due to the lack of vegetative cover, flash flooding, sheetwash and rilling are common. At certain times, intense rainfall events lead to large amounts of sediments to be mobilized in a short span. The stream gradients are steep, but the ephemeral nature of the flowing waters results in an imbalance between erosion, transportation and deposition. The streams can become heavily filled with sediments during sudden rainfalls. The drainage basins usually tend to be closed with internal drainage and basin sedimentation. 2. Desert hydrology. It is generally dominated by ephemeral streams. 99% of all desert drainages are ephemeral streams. They are streams that flow during seasonal or storm events. There are also perennial streams that flow all through the year. These streams are rare and sustained by water with headlands outside the desert region in a more humid environment. Examples are the Nile River with its headlands in the East African Rift Valley of Kenya and Uganda, that flows north to the Mediterranean through Sudan and Egypt. Lake basins. The perennial lakes are uncommon in deserts. Dry lake beds are common. Playa lakes found in deserts are dry lake beds. They are ephemeral and may periodically contain water. They also have high evaporation rates. Salt flats. The playa lakes contain a good quantity of dissolved salts. These precipitate salts on the lake floor when subject to evaporation. Pluvial lakes. These are perennial lakes. They are remnants of larger lake bodies that had formed in the past in the Pleistocene. These lakes are found in some desert areas such as Great Salt Lake, Pyramid Lake of Nevada. 3. Fluvial erosional desert landscape features. Fluvial erosion is the dominant landscape change process occurring in deserts. High rates of physical weathering by the fluvial process significantly changes the desert landscape. Let us see the different features. Differential erosion. This is the differential erodibility of different rock types under desert fluvial processes. For example, quartz sandstone is more resistant to weathering than shale rock. Due to this process, less resistant rocks are weathered and the more resistant rocks remain. A Butte Mesa desert topography. This is a result of differential erosion with resistant cap rocks holding up topographic features. This can be observed in areas with flat-lying sedimentary rock layers with alternating resistances to erosion. Rocks such as sandstone and limestone often form resistant cap rocks. These topographies include the following. 8. Environmental geology. Butte. They are round or oval-shaped, flat-topped topographic features. Mesa. They are elongated or table-like, flat-topped topographic features. Pinnacles. They are tower-like spires of rock, erosional remnants formed by cap rocks. B. Inselbergs. These are generally isolated, resistant rock masses that stand high in relief to surrounding topography. These topographies include the following. They are seen as erosion-resistant rock masses. They stand in relief as the more easily eroded rock material is eroded from the surrounding landscape. They are found along mature, dissected mountain fronts in deserts southwest. C. Pediments. They are gently inclined, concave up, ramp that extends outward from a mountain front, found along the lower slopes of mountains in desert regions. They are covered with a mantle of unconsolidated debris, or wind-blown sediments. D. Badland topography. They are intricately rilled and barren terrain in arid regions. They are mostly observed in areas underlain by horizontal strata of shale and clay formations that are poorly consolidated and subject to rilling and gullying. Badland topography is characterized by an extensive network of convoluted rills and gullies. 4. Fluvial deposition in arid landscapes. The debris that is eroded is mostly deposited on the valley floors in form of talus slopes and alluvial deposits. The depositional sites include pediment zone. This is the foot of the mountains. It is the zone at base of desert mountain ranges which forms the site of fluvial depositions from mountain canyons. Intermontane basins. This is the area of the internal drainage network. They are low areas between mountain ranges. They are sites of complex interactions between lake basins, aeolian processes, and fluvial regimes. The depositional features include alluvial fans. They are fan-shaped deposits of alluvial debris formed as mountain stream drainages empty onto the Piedmont area. The size of the alluvial fans is a function of the area of drainage basin, the climate, and the lithology of rocks in source area. Bajada. They are coalescing alluvial fans from adjacent mountain canyons forming a fan apron along the mountain front. 9. Environmental geology. Some important points. World's largest desert. It is the Sahara Desert in northern Africa. World's sandiest desert. This is the Arabian Desert in the Arabian Peninsula. World's hottest temperature. This is recorded at 136 degrees Fahrenheit in Sahara Desert in 1992 at Libya. Highest annual average temperature. It is recorded at 94 degrees Fahrenheit in Ethiopia, Sahara Desert. 9.7 Wind processes in deserts. Wind processes are very important and powerful forces which can help in shaping landscapes. Wind erosion processes like abrasion and deflation in deserts can change the landscape. These processes have the greatest impacts on dry soil areas as it is easier to transport light soil than wet soil. Further, deserts have less physical barriers, like hills, trees, which can reduce the wind erosion processes. The landforms shaped by wind processes include rock pedestals, deflation hollows, oases, sand dunes, yardangs, and desert pavements. Wind erosion. Wind erosion is the process of breaking down and dispersing particles by wind movement. It occurs by 3 different methods, namely abrasion, deflation, and attrition. Wind abrasion. This is the process of the abrasion of an object due to the impact of particles carried by the wind. It results in wearing away of an object due to the impact of particles transported by wind action. This can cause the object being hit with particles to become smooth. It is similar to sandblasting. The places most affected by this activity are those areas where there is less vegetation. Ventifacts are structures that have become smoothened by sand particle abrasion. In deserts, the wind abrasion processes can also result in ridge and furrow landscapes such as in Bahrain. Wind deflation. It is the erosion of soil due to the removal of sand, dust, rocks by the action of wind. Due to this, the surface of the desert becomes rocky, consisting with gravel-sized particles. Wind attrition. It is the process in which wind-borne particles collide with each other and wear out in the process. 10. Environmental geology. Wind deposition. The important features deposited by wind are sand dunes. Also, loess are deposits of finer sediments. Sand dunes. They are composed of a variety of minerals due to limited weathering. The dune sands are uniform in size and shape. Generally, sand dunes form when there is an abundant supply of sand and steady winds. Sand dunes slope gently in the upwind direction. The wind blows sand into a network of troughs, crests, and ripples that are perpendicular to the wind direction. They are the consequence of saltation. Accumulations of sand build into mounds and ridges, and they become a dune when the slip face is about 30 centimeters high. Dunes grow as sand particles move up the gentle upwind slope by saltation and creep. They fall onto the slip face, inducing movement. The wind deposits dune sands layer by layer, and when the wind changes directions, cross beds are formed. They are named cross beds due to the way each layer is formed at an angle to the ground. The sand dune type is related to the quantity of sand available, the direction of the wind, and nature of the ground. Sand dunes can be crescent-shaped, star-shaped, parabolic, linear, or Barchan. Loess. The silt and clay deposited layer-wise due to wind action form loess. These deposits make very fertile soils in many regions globally. Sand sheets. These are flat areas of sand with sand grains that are too large to saltate. 45% of depositional surfaces are of this type, e.g. Salima in South Egypt. Deflation hollows. These are formed as a result of removal of fine particles by the wind, lowering the surface and creating a hollow. Qattara Depression is an example of this formation. 9.8 Life forms and adaptations in deserts. Desert ecosystems have well-adapted flora and fauna. The plants have many adaptations to survive the dry conditions. Desert plants. The plants found in deserts can be classified as annual, ephemeral, and perennial species. The desert plants can also be classified according to how they survive high temperatures and how they survive uncertain precipitation, drought escapers, drought evaders, and drought resistors. The plants found in deserts are called xerophytes. Cacti are drought resistors. The desert cactus has spines that help cool. 11. Environmental geology. The plant and protect it from the hot sun. Cacti also store moisture in their spongy stems or root tissues during periods of rain and use it during dry periods. The leaves are reduced to spines in the big wide green cortex, which is the stem, functions as the leaves, carrying out photosynthesis. Some plants like mesquite trees have long tap roots, over 100 feet, that help them reach the groundwater. Some plants compete with each other for water. The plant creosote produces toxins and releases them so other plants cannot survive in that toxin-affected area. This process is referred to as allelopathy. The creosote is also a drought resistor. They have tiny leaves and their leaves are often coated with a waxy, resinous substance to reduce the loss of water. These are some adaptations of desert plants. Let us now study about the desert plants. Annual plants. These plants are mostly herbaceous and have a life cycle of less than a year. Some examples include Panicum turgidum. The desert annual plants are therophytes as their life cycle is just a few weeks and they are dormant as seeds to survive dry, harsh conditions. Ephemeral plants. These have a very short life cycle. An example is Alyssum ellipsoides. These plants are born after occasional rains and reproduce and die before a new drought season. Perennial plants. These plants survive in dry conditions by the minimal loss of water during the hottest periods. These plants are xerophytic. They have leaves that are leathery and coated with wax. The stomas are closed to reduce transpiration and evaporation. Most plants have a reduced foliar surface and the leaves are converted into thorns as adaptation strategies. Members of Cactaceae and Euphorbiaceae family belong to this group. Also members of the Phretophytes, which have extremely long roots to take water from the groundwater, belong to this group. B. Animals of the desert. Animals also adapt to the dry conditions according to the availability of water, food and survival in the extreme weather conditions. Estivation. During the drought periods and heat, some desert animals estivate. These desert animals can escape drought by sleeping through the drought period. This dry weather, sleep, is called estivation. For example, spadefoot toads sleep in underground burrows for months or years covered with a jelly-like substance that keep them moist. The heavy raindrops that cause ground vibrations wake them up. Estivating animals include some species of reptiles and the desert snails. They can remain dormant, i.e. the snails can remain in their shells as long as 5 long years. 12. Environmental geology. B. Resistant eggs. Some desert animals are able to complete their life cycle in short periods. They produce many tough and resistant eggs which tolerate years of heat. The eggs hatch after heavy rainfall. Examples are the crustaceans, triops called as shield shrimps, that are found in the Australian deserts. C. Migration. Some animals migrate to different areas. Birds inhabiting deserts migrate to avoid the harsh conditions. They come back when the season is favorable for them. They breed after rainfall. In the some animals migrate to different areas. Melopsidicus undulates travels thousands of kilometers during extremely dry seasons and return later. D. Nocturnal activity. Animals also rest in shade during daytime and carry out fewer activities. Many desert animals avoid the daytime heat and live in cool, deep burrows underground. E. Soaring. Some birds soar high above where temperatures are much cooler. Examples include hawks, vultures, and eagles. F. Big ears and long legs. Some desert animals have bog-oversized ears that help to cool the body by radiating heat. In these animals, the blood vessels in the ears are located just under the skin, and as air flows around them, it cools the blood. The cooled blood helps to cool the body. Examples are jackrabbits, desert foxes, camel and gazelle. G. Adaptations of the camel. The camel is known as the ship of the desert. It can survive extreme heat and dry deserts. It has a number of adaptation strategies to survive in the hot deserts. It conserves water by excreting concentrated urine and dry feces. It stores fat in their hump for food so they can survive long periods without food. The camel has long eyelashes that protect the eyes and nostrils, which can be closed during sandstorms. It has a thick coat of fur and underwool that keep them warm during cold desert nights and also insulate them against the scorching day heat. It can lose up to 25% of its body weight when there is no water availability and rehydrate when there is water availability. A camel can drink up to 150 liters of water in 10 minutes when there is water availability. It can also survive when its body temperature increases up to 12 degrees Celsius. The fossils of dinosaurs in the Gobi Desert. The Gobi Desert 130 million years ago was a region full of life. Paleontologists have found very interesting fossils from the Cretaceous period when dinosaurs were dominating. Out of the 7 systematic groups in which dinosaurs are classified, fossils belonging to 5 groups have been found in the Gobi Desert. The fossils here show the evolution of dinosaurs from the unopened eggs and even the remains of young dinosaurs just out of their eggs. 13. Environmental geology. 9.9 Anthropogenic factors leading to desertification. We have so far learned how deserts are formed naturally. Human beings can induce or accelerate the desertification process in many ways. Overgrazing, deforestation, poor irrigation techniques, etc. can lead to desertification. Approximately more than 110 countries have drylands which are potentially at risk from desertification. This can affect almost 900 million people. A. Overgrazing. This is unsustainable grazing. It occurs when the number of cattle, goat that can graze an area exceeds the carrying capacity of the land. When this capacity is exceeded, changes in vegetation occur. For example, drought-resistant species replace edible species. Also, the soil quality is reduced. The animals break down the soil structure, thus increasing its vulnerability to erosion. B. Overcultivation. This occurs when more food production is required to feed large populations. C. Deforestation. This occurs when forests are cleared for agricultural purposes and also for fuelwood. It leads to desiccation of the soil and lowered water tables. D. Inappropriate irrigation practices. Poor irrigation techniques can result in reduced soil fertility. This is due to salinization and waterlogging. 9.10 Combating desertification. The United Nations Convention to Combat Desertification, UNCCD, 2006 is an international treaty that aims to promote effective action through innovative local programs and international partnerships. More than 1 billion people have little access to water, and by 2030 the demand will increase by 30%. This can displace 700 million people by 2030. So land degrading practices should be discouraged and sustainable land use practices should be followed. The World Day to Combat Desertification and Drought is observed on 17th of June annually. This date is the day the General Assembly adopted the Convention to Combat Desertification, which is the sole legally binding international agreement linking environment and development to sustainable land management. The importance of observing this day is to make the public aware of land degradation, work for improving the conditions for people living in the drylands, to restore soil productivity, and to address drought mitigation. This can be achieved by involving the local people as a participatory approach in addressing the problems related to desertification and land degradation. 14. Environmental geology. 9.12 Summary. In this unit we have studied about deserts, types of deserts, various fluvial and wind processes that occur in deserts. We have also understood the different life forms, both plants and animals, and their adaptations in desert regions. We have further learned that human activities can also cause desertification, and we should follow sustainable land practices to combat anthropogenic desertification. 3. Environmental Geology. Module 10. Hydrogeology and Hydrologic Cycle. 1 Introduction. Air is a mixture of gases. The principal among the gases are nitrogen, 78% by volume, oxygen, 21% by volume, argon, 0.95% by volume, carbon dioxide, 0.034% by volume, and a variable amount of water vapor. The amount of water vapor in the lower range of the atmosphere can vary over a wide range from about 0.05% to almost 4% by volume. Fig. 1 pie diagram showing distribution of gases in atmosphere. The water vapor present in the air is an important causative factor for the formation of mist, fog, clouds, rain or snow. The carbon dioxide plays a role in plant life and overall climate of the Earth. Presence of ozone in the atmosphere in the altitude ranging between 20 to 30 km above the Earth's surface absorbs all the ultraviolet radiation from the sun, where otherwise it would have been detrimental to plant and animal life. The atmosphere, particularly with water vapor and carbon dioxide change, the incoming solar radiation, reaches both the land and ocean at the Earth's surface. With the increase in carbon dioxide content, the radiation would be more and the Earth become warmer. P. R. Pisharoti, a pioneer in Indian meteorology, has in his book, Meteorology for the Indian Farmers, special publication, Indian Space Research Organization, Bengaluru, September, 1986. 4. Environmental Geology. Has comprehensively dealt about the solar radiation, its interaction with the atmosphere, structure of the atmosphere, and the variations of pressure and temperature with altitude. He has outlined how horizontal pressure differences on a rotating Earth, primarily caused by temperature differences, generate winds. He also has described the physics of clouds and rain or snow. He has given an outline of different weather systems which has regional impact. Fig. 2 Conversion of solar radiation into heat energy. Water in the planet Earth, occurring in liquid, solid and gaseous status, displays varied degree of motion. The hydrological cycle, also known as water cycle, defines the movement of water and storage of water in Earth. Agriculture is strongly dependent upon weather. Human survival is dependent on water availability. Seasons impart a rhythm to life of the Earth. The sequence of events in hydrologic cycle appears to be simplistic. But, in reality, the hydrologic cycle is a vast and complicated cycle which involves a large number of paths of varying time scale. It is a continuous recirculating cycle. It has neither a beginning nor an end. Subramanya, 2013. 5. Environmental Geology. 2 Objectives. 1. Explain stages of hydrological cycle. 2. Describes the various factors affecting hydrological cycle. 3. Narrating the importance of hydrological cycle. 4. Describes the movement and circulation of water on Earth. 3. Concept map. The components of the hydrological cycle: evaporation, condensation, precipitation, runoff. 6. Environmental Geology. Fig. 3 The water cycle. 4 descriptions. 4 to 1 Hydrological cycle. The hydrologic cycle begins with the evaporation of water from oceans and lakes. Evaporation is the change of water form from a liquid stage to a gaseous one. The largest movement of water in the water cycle is the evaporation of water from the oceans. Evaporation of water from the warm surface of oceanic body results in increased amount of moisture in the colder, drier air immediately above. As water vapor moves up, it gets cooled and condenses into clouds. Condensation is the change of water form from gaseous form into liquid form. Condensation occurs in atmosphere when warm air raises, cools and loses its capacity to hold water vapor. When water vapor condenses, it becomes droplets in the cloud. The upward motion that generate clouds can be the result of convection in unstable air. Convection is the result that happens when the land surface is hot, the overlying air. 7. Environmental Geology. Which warms up becomes less dense than the air in the surrounding parts and attains motion in a vertical direction. When surface winds are deflected by friction towards the center of the low-pressure surface, it would result in extratropical cyclones. Surface convergence can generate rising motion, leading into condensation of water vapor. Fig. 4 Hydrological cycle and distribution. The huge quantity of evaporated water, in one form or the other, moves around the globe until it returns to surfaces, precipitation. The precipitation is the primary natural mechanism of water transportation from the atmosphere to the surface of the Earth. It may include rain, hail, snow and freezing rain. While much of the clouds get back into the oceans and lakes as rain, some part of it, when driven by wind onto the land, precipitate into rain, snow, hail, etc. A well-developed, extratropical cyclone can generate any or all forms of precipitation. With continued evaporation, water. 8. Environmental Geology. Vapor in the cold part of atmosphere condenses to form ice crystals. It is said that the atmosphere keeps water for an average of 9 days before it releases it down as rain. Fig. 5 Diagram depicting annual water budget. The boundary between air masses front can either be warm, cold or stationary. In case of cold front, a colder, denser air mass lifts the warm moist air ahead of it. As the air rises, it cools and the moisture in it condenses to produce clouds and precipitation. Due to steep slope of a cold front, vigorous rising motion leads to formation of showers and occasionally severe thunderstorm. In the case of warm front, the warm, less dense air lifts up the colder air ahead. Again, the air cools and its moisture condenses to form clouds. Precipitation that develops in advance of a surface warm front is typically steady and widespread than precipitation associated with a cold front. 9. Environmental geology. Fig 6 flowchart of drainage basin is an open system. Inputs into the drainage basin include energy from the sun for evaporation, precipitation, rain and snow. Outputs move moisture out of the drainage basin and include evaporation and transpiration from plants, collectively called evapotranspiration, runoff into the sea. Water percolating deep into underground stores where it can be effectively lost from the system. Stores of water. On the surface, glaciers, lakes, rivers, puddles. 10. Environmental geology. Vegetation stores water by interception and plants. The soil can hold water. Groundwater is stored in permeable rocks. Transfers and flows moves water through the system and enable inputs of water to be processed from one store to another. Transfers include through fall, stem flow, infiltration, through flow and groundwater flow. Fig 7 flowchart of water budget. While almost all the water is contained in oceans, only 3% is the fresh water available on land surface, and of that 3% almost 69% is trapped as glaciers. Glaciers can keep water trapped as ice for thousands of years. The lake effect snowfall is caused when cold wind blows across a large lake. The intensity of snowfall can get enhanced due to additional lifting of clouds in mountainous terrain. Once the snow begins to melt, the water absorbed by the ground becomes groundwater or returned to the lake, ocean as runoff. The water through precipitation when reaches the ground, some part of it evaporates back into the atmosphere, some part gets consumed by the vegetation and a part saturates the soil, infiltrate and percolate into ground as groundwater. The part of water consumed by vegetation reaches the atmosphere as transpiration. Groundwater may as springs and or base flow reach the path of the stream. Rest of the precipitation, as overland flow, largely finds its course into the streams and rivers as runoff. The stream river water flow ultimately gets emptied back into lakes and oceans. Thus, as Subramanya 2013 puts, the total water resources of the earth are constant and the sun is the source of energy for the hydrological cycle. The main components of the hydrologic cycle can 11. Environmental geology. Broadly be classified as transportation component and storage component. The transportation components include precipitation, evaporation, transportation, flow, infiltration and runoff. Storage components are that of storage on the land surface, like ponds, lakes, reservoirs, etc., soil moisture storage and groundwater storage. The Horton's representation of the hydrological cycle illustrates the storage and transportation components and their relative positions in the cycle. Fig 8 typical hydrological cycle in flowchart form. The hydrological cycle has an influence on agriculture, forestry, geography, etc. Human interference in the hydrological cycle, like through artificial rain, change of vegetal cover, change in land use, indiscriminate extraction of groundwater, etc., can cause serious repercussion in the fields of agriculture, forestry, geography, etc. It has its immense application in the design of projects about water supply, irrigation and drainage, flood control, coastal geomorphology and geohydrology. 4-2 El Niño. In the tropics, where weather is warm year-round, rainy seasons known as monsoons alternate with dry period. But, the rhythm of the seasons cannot be relied upon. The tropical Pacific Ocean and global atmosphere disrupts normal patterns of climate and life. The alternation between the normal climate and a different recurrent set of climatic conditions in the Pacific region is called El Niño. The term, El Niño, was originally used by fishermen along the coast of Ecuador and Peru to a warm ocean current appearing around the period of Christmas over several months. 12. Environmental geology. During 1920s, Walker, who was on assignment to India, trying to find a way to predict the Asian monsoon, discovered a remarkable connection between barometer readings at eastern and western sides of the Pacific. He notified when pressure rises to the east, it usually falls low in the west and vice versa. Walker coined the term, southern oscillation, to the ups and downs in that east-west seesaw in southern Pacific barometer pressures. Fig 9 typical winter time pattern, El Niño. 13. Environmental geology. Fig 10 diagram showing formation of El Niño. When the seesaw is in its high index, strongly tilted state, pressure is high on the eastern side of the Pacific and low on the western side. Along the equator, the east-west pressure contrast drives easterly, east to west, surface winds from the Galapagos Islands nearly all the way to Indonesia. When seesaw switches into its low index, weakly tilted state, the easterly surface winds weaken. The biggest changes in the slope of the seesaw and in the strength of the easterlies occur over the western Pacific. To understand how El Niño affects the ocean, it is necessary to learn how surface winds move water during normal years and how the resulting motions affect water temperature. The easterly winds that blow along the equator and the southeasterly winds that blow along Peru and Ecuador coasts both tend to drag the surface water along with them. The Earth's rotation then deflects the surface currents northward in the northern hemisphere and southward in the southern hemisphere. The surface waters are therefore deflected away from the equator in both directions and away from the coastline. Where the surface water moves away, colder nutrient water comes up from below to replace it, and this phenomenon is called upwelling. Both the equatorial upwelling and the coastal upwelling are concentrated in narrow regions of around 150 kilometers wide. The winds that blow along the 14. Environmental geology. Equator also affect the properties of upwelled water. In the absence of the wind, the dividing layer between the warm surface and the deep cold water called thermocline would be nearly flat, but the winds drag the surface westward, raising thermocline up to the surface in the east and depressing it in the west. The winds control the upwelling. The winds are also responsible for the cold tongue in the sea surface temperature pattern. But the resulting changes in the sea surface temperature will in turn have effects on the winds. When the easterlies are blowing at full strength, the upwelling of cold water along the equatorial Pacific chills the air above it, making it too dense to rise high enough for water vapor to condense to form clouds and raindrops. As a result, this strip of the ocean stays conspicuously free of clouds during normal years, and the rain in the equatorial belt is confined to the extreme western Pacific near Indonesia. But when the easterlies weaken and retreat eastward during the early stages of an El Niño event, the upwelling slows and the ocean warms. The moist air above the ocean also warms. It forms deep cloud, resulting in heavy rain along the equator. The change in ocean temperature thus cause major rain zone over the western Pacific to shift eastwards. Related adjustments in the atmosphere cause barometer pressure to fall over the central and eastern Pacific and rise over India, Indonesia and Australia, thereby resulting in eastward retreat of the easterlies. Thus, it is difficult to identify the subtle change in the ocean atmosphere system that initiates a transition into or out of El Niño condition. The twists between ocean and atmosphere can have ripple effect on climatic conditions in the far regions of the globe. Dense tropical clouds distort the airflow aloft, 8 to 16 kilometers above sea level, but on a horizontal scale of thousands of kilometers, the waves in the airflow in turn determine the positions of the monsoons. The impact of El Niño upon climate in high temperature latitudes show up more clearly during winter time. 5HYDROGEOLOGY. Hydrogeology is the subject that deals with distribution and movement of groundwater in the soil and rocks of the Earth's crust. Merriam-Webster defines hydrogeology, more appropriately, as a branch of geology concerned with occurrence, use and functions of surface water and groundwater. Hydrogeology is the study of water contained in materials of Earth's crust, its origin, evolution, physical and chemical characteristics, and ultimate destination. The terms groundwater hydrology, geohydrology, and hydrogeology are used interchangeably. While hydrogeology is the term commonly used by geologists and hydrogeologists, the term geohydrology is most often used by 15. Environmental geology. The civil engineer. Whether it is called hydrogeology or geohydrology, the meaning remains almost equivalent. Hydrogeology is an interdisciplinary subject and deals on chemical, physical, biological, and legal aspects of surface and groundwaters. The subject of hydrogeology, apart from various science faculties like of agriculture, horticulture, soil, civil engineering, etc., has also a larger bearing on urban, forest, and coastal hydrology. Fig. 11 Interaction of hydrogeology with other geocomponents. Hydrogeological features mainly dependent upon geology, geomorphology, and climatology of an area. The rainfall distribution both in space and time, intensity, frequency, and variability is of considerable importance for understanding hydrological aspects of any given area. In a virgin unaltered landscape, after a dry rainless period when rainfall occurs, a good part of it will be lost through evaporation. Subsequent rains form part of the surface runoff. A rapid runoff would mean minimum percolation into the earth even if the rains are normal. Saturation runoff occurs after soil. 16. Environmental geology. Water zone is fully saturated. Infiltration of water is the downward movement of water from the ground surface. The maximum infiltration rate is the infiltration capacity, or F capacity. Surface flow in a natural landscape appears when the water availability exceeds the F capacity. Infiltration of water is distinct from percolation. The water percolation is the transit of infiltrated water by gravity through the zone of aeration to the zone of saturation. In case of hard rocks, the water percolates through weathered mantle that constitutes zone of aeration and/or fractures. The water contained in materials of Earth's crust is groundwater, and this quite often spelled by many as groundwater. When groundwater is not near to the Earth's surface, there forms a zone in where majority of open spaces are with air. This is called zone of aeration, or vadose zone. Vadose zone, which is the zone of aeration, is the part of Earth between the zone of saturation and the ground surface. Vadose zone has a pressure head less than atmospheric pressure. The vadose zone does not The water contained in materials of Earth's crust is groundwater, and this quite often spelled by many as groundwater. When groundwater is not near to the Earth's surface, there forms a zone in where majority of open spaces are with air. This is called zone of aeration, or vadose zone. Vadose zone, which is the zone of aeration, is the part of Earth between the zone of saturation and the ground surface. Vadose zone has a pressure head less than atmospheric pressure. The vadose zone does not include the area that is with water content above the water table, and this is referred to as capillary fringe. The capillary fringe is the result of the process of capillary action. Movement of water within the vadose zone involves study of soil, hydrology, and hydrogeology. Groundwater recharge under natural process occurs through vadose zone. To put it in brief, the vadose zone is the subsurface unsaturated or undersaturated part of the geological rock formation that lies above the groundwater table. In marshy zone, the vadose zone may be absent. Rate of water percolation and groundwater recharge is dependent upon the rock characteristics in the vadose zone. When there is impermeable rock in the zone of aeration, downward movement of infiltrated water gets blocked or restricted, resulting in the saturation of the interstices of the rock material above the impermeable barrier. Water in such a zone is called perched groundwater. The upper surface of the zone of saturation is the water table, or phreatic surface. In other words, the area separating the vadose zone and the phreatic zone is water table. The water table fluctuates between seasons. Some use the term phreatic zone in preference to zone of saturation. The part of the geological rock type, be it alluvium or hard rock, when the pore spaces, fracture zones in them are filled with water that is infiltrated and or percolated, forms the zone of saturation, and this zone of saturation is the one between the water table and the depth at which the rock type can no more hold and transmit water because of impermeable characteristics. In other words, the lower limit of zone of saturation extends to such depths at which the interconnected openings remain absent or negligible. 17. Environmental geology. Fig. 11 Stages of formation of groundwater. An aquifer is the rock formation or part of rock formation which yields appreciable quantity of groundwater. Every aquifer has a capacity to store water which is expressed as coefficient. The storage coefficient, which is otherwise called storability, is defined as the volume of water that can be released or taken into storage per unit surface area of the aquifer per unit change in head. In the case of water table aquifer, otherwise called unconfined aquifer, which is bound at the top by the water table, coefficient of storage is analogous to specific yield. The specific yield is the saturated part of the rock to drain water under the force of gravity. It is expressed as percentage volume of water yield by draining a saturated rock to its total volume. The specific yield of rock is complementary to the specific retention. In case of hard rocks, the intergranular space, rock matrix, and the openings like joints, fractures largely are the factors that govern the specific yield. The rock matrix, when porous and permeable, and the joints, fractures together, form double porosity characteristics. If the rock matrix is hard, massive, non-porous and not permeable, in such cases fractures, joints when are present, will act as water conduits. Rock will not be an aquifer when with its extensive spread are massive, hard, non-porous, not permeable, and fractures, joints are absent. In case of clay formations, though they are highly porous, are not permeable. The semi-confined. 18. Environmental geology. Aquifer condition prevails when the confining layer is semi-permeable. A confined aquifer is the one which will be overlaid and underlaid by impervious and impermeable rock formation. Fig. 13 Types of aquifers. Depending upon the capacity of the aquifer to accept, store and or transmit water, the rainwater and or water from any other source that infiltrates, when reaches the upper surface of the vast massive rock zone or impermeable bed, finding no scope to further percolate, gets into the process of gradually saturating all the fractures, joints and any other voids or intergranular pore space in an ascending manner. With this process on, depending upon the rate and quantity of water that infiltrate, the interconnected fractures, joints and any voids in the semi-confined, semi-unconfined and unconfined aquifer zones gradually get saturated. Groundwater recharge is dependent upon the porosity and permeability of the soil and underlying geological formation that prevails in the area. Porosity is the pore space between unconsolidated soil and other earth material, weathered and or fractured part of the rock. Permeability is the expression of the connectivity of pores to permit the water movement. This process of saturation from semi-confined to unconfined aquifer zone is possible only when the net annual draft component from the aquifer is less than the net annual groundwater recharge. Thus the unconfined aquifer, semi-unconfined aquifer and semi-unconfined aquifers which are transitionally interconnected form a composite aquifer system, more so in a hard rock terrain. Recharge to the composite aquifer system will be through the unconfined aquifer. 19. Environmental geology. When bore well taps unconfined, semi-confined aquifer, the water in the well rises to a particular level and the water level attained under such a condition is called piezometric surface. The piezometric surface or piezometric level will be dependent upon the hydrostatic pressure that sustains in the aquifer. The fluctuation in the piezometric surface is dependent on the variation in the hydrostatic pressure of groundwater within the aquifer. When the storage coefficient value S and fluctuation in piezometric surface H is known, the quantity of water added or released from the aquifer can be calculated. Darcy's experiment in 1850s led to determine the rate of flow of groundwater. Darcy's law states that the amount of groundwater discharged through a given portion of aquifer is proportional to the cross-sectional area of flow, hydraulic gradient and hydraulic conductivity. It is expressed as K equals Q AI, where Q equals quantity of water discharged in unit time. A equals total cross-sectional area through which water percolates. I equals hydraulic gradient. Fig. 14 diagram depicting Darcy's law. Permeability of a rock is its capacity to transmit water under differential pressure and is measured by the rate at which it will transmit water through a unit cross-section under unit pressure differential per unit distance. Rocks that lack porosity do not transmit water and are hence referred to as impermeable. 20. Environmental geology. Porosity thereby is not a measure of permeability. Permeability was then understood to be a field coefficient at the prevailing temperature of water. It is later the term, hydraulic conductivity, used in preference to coefficient of permeability. The capacity of a saturated rock to retain water after the drainage is specific retention. The quantity of water that will drain from a rock depends on the duration of drainage, temperature and chemical capacity of water. The specific yield is the capacity of a saturated rock to drain water under the force of gravity. It is expressed as percentage volume of water yielded by draining a saturated rock to its total volume. The groundwater resources can be categorized as dynamic reserve and static reserve. The dynamic reserve represents long-term average annual recharge under the condition of maximum use. Static reserve is the groundwater contained within the permanently saturated zone of the aquifer and that represents the total groundwater reserve minus the dynamic reserve. When the groundwater draft exceeds the normal annual replenishment and static resources are exploited in any manner, it amounts to mining of groundwater, and a time may come where it no longer is a sustainable resource. Once groundwater is contaminated, it becomes a costly issue to clean up.